Hi everyone, welcome to the talk on Kubernetes QoS for Kubernetes Trap Pods. My name is Vinay and I work for Futurewei Technologies and Syspengdu. I've been working, sorry. My name is Vinay and I work for Futurewei Technologies. I'm an architect there and I work on Kubernetes compute and networking. My interests are in those areas and I work with lately with eBPF as well. And in my free time, I do some ski instructing for little kiddos. And Phu, could you please introduce yourself?
Yeah, my name is Phu Tran. I also work at Futurewei as a software engineer. I also work in the Kubernetes and networking field. And in my free time, I like to hang out with my pets. I have a ragdoll and a miniature Australian shepherd. And I'll pass it back to Vinay to introduce the agenda for today.
Thank you, Phu. So today we'll look at how we'll bring Kubernetes currently does not have any notion of quality of service for the pods. And this talk is about bringing that. And we'll start with an overview of what QoS and network traffic means. And we'll look at the Mizar, we'll look at what XDP and eBPF bring here, and look at what Mizar data plane looks like, a brief overview. And we'll look at our use case, then followed by the design that we have to solve this problem of bringing QoS for Kubernetes pods. And we'll do a demo. Hopefully it'll go well with the demo gods smiling on us. And we'll open it up for Q&A after that. So quality of service and network traffic, it boils down to the basic fact that all the traffic that you have, they're not born equal. There are some traffic like real-time applications like Zoom and FaceTime, Google Meets. They need low latency. They use a certain amount of bandwidth. They're not bursty, but they use that bandwidth. This we call like real-time classification, and then the second is streaming audio. If you stream YouTube videos or you go to Netflix and stream a movie, then you get receive-side buffering. So those applications can tolerate a little bit of loss, but they do require guaranteed bandwidth. And lastly, you have data traffic. That is traffic that's coming from email or your file backup of those kind of applications, which don't really need any bandwidth guarantees, but as long as the data gets there in a reasonable amount of time. So those are the different types of traffic that we are going to look at today. And with that, I'll pass it to Phu for talking about eBPF, what it is.
Yeah, so eBPF is one of the core technologies that we use in Mizar and in the QoS demo that you'll see today. It allows for us to run programs safely in the Linux kernel. Its current usages include networking, security, observability, and tracing. It's actually deployed in production today, even though it's relatively new. It's used at Cloudflare, Netflix, Facebook, etc. There's actually work in progress to, at Microsoft, have eBPF on Windows. Some example use cases of eBPF are packet inspection, performance analysis using trace points and kprobes, security monitoring, network load balancing, and firewalling. The safety of the eBPF program that you load into the kernel is guaranteed by the verifier at load time. It disallows things such as unbounded loops or programs that are too big. It also provides an easy API, an easy fixed API into the kernel via this thing called the BPF helpers. And another technology we use alongside BPF is XDP. XDP is a kernel hook point on the RX path in which you can attach a eBPF program to. This hook point happens before the SKB is even allocated, so it allows for extremely efficient packet processing. It's not necessarily a kernel bypass, so we can still rely on all the useful features of the kernel. The actions that we used are, XP has these things called actions in which you can do things with the packets. These actions include XBTX, where you can send the packet back out the same interface in which you received it. XDP redirect, in which you can send the packet to a different interface. XDP pass, where you can send the packet to the network stack. XP drop, where you can drop the packet. And XDP abort, where you drop the packet, but it's because of an error in your program or something. And Mizar is the container network plugin that we wrote for Kubernetes, utilizing both eBPF and XDP. It provides multi-tenant networking alongside Arctos, which is another fork of Kubernetes that we develop at Futurewei. It allows for multiple VPCs and subnets. We used Geneve as the overlay encapsulation protocol, And with its variable length header, we implement things such as network fast paths and load balancers. This is a very basic diagram of the node architecture for Mizar. We run this node agent called the transit daemon, which is responsible for relaying information between user space and kernel space via the eBPF maps. There are two types of XDP programs in Mizar, one on the RX side and one on the TX side. And with these two programs, we are able to process and direct packets via the BPF maps. And now I'll pass it back to Vinay to talk about how we use QoS in Mizar.
Okay, so before we look at our use case, let's take a brief overview of what QoS is in the network. So when you think about an application, you just start up YouTube and you're streaming a video, it's streamed to you from some server. The data packets, they pass through a network of switches, and these switches are all enforcement points for QoS. They can differentiate between types of traffic and give certain type of traffic more priority and lower latency pathways than the others without queuing. At the egress, you can use different kind of algorithms to limit the rate at which the traffic goes out, token bucket or fair queuing, EDT, which we'll talk about later. And at the ingress, you can also rate limit for traffic. If the traffic is overwhelming the application, it's not able to keep up, then we can use rate limiting techniques. We're going to leverage some of these techniques in our talk today. Let's take a look at the use case here. This is a fairly dumbed down, simple scenario where you have one VM and there are two pods in here which are sending traffic. One of these pods is backing up some kind of data or processing logs and storing it to a disk. And the other one is handling payment processing. It's processing payment requests from a point of sale terminal at some store at the edge. Now, clearly, one of these pods has more important things to say, but they're competing for the same bandwidth. And in the interest of fairness, if we drop the packets that are being sent by the payment processing pod, that will manifest as long lines at your checkout queue. And the people at the back of the queue might just queue up and say, oh, I'm going to go home and come back later. That's loss of business for the store, which is not a good thing. But there is a way out. We can do better. So now let's take a look at this same picture. We have the same VM, but we introduced Mizar, our Mizar transit daemon that Phu just described. Now, what this daemon does is it watches for Kubernetes pods that are scheduled on the node, and it looks at the annotations on the pod, and it's able to tell from that, okay, this pod is high priority traffic, this is best effort. And when it sees that, it programs BPF maps in the kernel. And those maps that are programmed in the kernel allow eBPF, the XDP programs that we attach to the vEth pairs here, in the case of the high priority pod as well as the low priority pod. They can look up, okay, this is coming from the pod that's marked high priority, so I'll send it down the redirect path, the fast path, which is XDP redirect, that takes the packet and deposits it into the TX queue of the transmit NIC. For the low priority traffic, it takes the path of going down the hardware stack where it uses XDP pass, and it sends it to the network stack, where we enforce prio scheduling for prioritization, and rate limiting for best effort. So with these, we have the tools to be able to create a rich set of classifications, and that would look something like this. We came up with 3 different classes called premium, expedited, and best effort. And in these 3 classes, we have high, medium, and low priorities. So given that we have these, we're able to let the user classify their applications. They can say, okay, real-time traffic like Zoom or your Google Meets, any of these video calls that need low latency and high priority, they're classified as the highest priority class. Then you have the expedited, which is your streaming applications, and best effort, which is like file backup emails, which don't really need any kind of guarantees. So given these, we can implement quality of service, we can differentiate between the traffic coming out of the pods and implement prioritization at the egress of the host. But what about the network? So as we talked about in the earlier slide, all these routers and switches, they understand IP packets which are tagged with a certain, it's called DSCP codes in the QoS bits of the IP packet. And when we tag them with certain values, the network treats those packets differently. So we have the highest priority traffic doesn't incur any queuing and it's sent out, so those are low latency. And the best effort traffic is generally queued and sent out later or dropped if there is too much traffic. And this gives us the end-to-end QoS capability for our pods. And one thing to note here is that we implemented for the best effort traffic at the egress host dynamic rate limiting, which is based on the earliest departure time algorithm, called EDT algorithm. And the best way to think about this algorithm is think about a train station. You have trains leaving, and the more frequently the trains leave, the more people it can get out of the station. It's the same thing that you map into the packet world. So the more packets that leave the egress host in a given amount of time, the more data, the more bytes are transmitted. And when a packet comes out from the best effort pod, we can timestamp it. Okay, this packet is going to leave at 1 second. And the next packet is going to leave at 5 seconds, the next at 9. And if you space them out farther apart, the rate is lower. So this allows you to configure the rate at which a certain, the low priority traffic leaves the host. And that is achieved by this bandwidth monitor a thread that runs in the Mizar daemon. What it does is it polls the statistics of the transmit packets that are sent out by the high priority pod as well as the low priority, the best effort pod in this case. And if it sees that there is high priority traffic activity, it adjusts the rate so that the best effort traffic gets a lower bandwidth availability for them. But if there is no high priority traffic, like your applications are silent, the streaming application, there's no payment traffic coming in, then it adjusts the rate back up so that the best effort traffic can use whatever available bandwidth is there to it. That way, we don't waste bandwidth. So with this, we still need a way for the user to tell us how to classify the pod, how do you tell what kind of pod it is. So we defined a couple of annotations. The network class lets you define the class of the traffic, which is, as we saw earlier, the 3 classes that we have, best effort, expedited, and premium. In this case, what you're looking at is a pod that says, okay, my traffic is expedited of medium priority. Now, let's get to the demo, and I'll have Phu take a look at describe the demo and then do the demo.
Yeah, so on a single VM, we'll have 3 senders representing 3 different traffic classes. Best effort, you can think of as maybe a cloud backup for your phone or your laptop. The second class, expedited, you can think of as maybe like watching Netflix. It could get blurry, but it's not that big of a deal. And as for premium, you can think of as like money transactions. If you don't get that direct deposit, it is a big deal. The demo will consist of 2 parts. Part 1 will have 3 senders simultaneously send push data at the same time, and we'll see how the bandwidth for each of the sender is handled. For part 2, we will start the best effort traffic first, and then we'll start the premium traffic to see the best effort preempted. And now let's go to the demo. All right, so we have a bunch of windows here. The green window represents the premium traffic. The yellow window represents the expedited. And the white window represents the best effort. I'm just starting all these senders and receivers. The receivers are on the right side, the senders on the left side, and they're actually waiting for me to write this file before starting the test. So now we will create this file, and the traffic will start. So as you can see, on the top, we have premium at around 1.4 gigs per second. In the middle with the yellow, on the right side and receiver side, we see expedited with around 1.3, 1.25. And then finally, at the bottom, we have best effort at, yeah, it's about the same rate for some reason. Wait, did we send the right one here?
No, I don't think we started something. Let's just go to the video, the demo video. Sorry, we're gonna have to fall back to the demo video. I think one of the pods is not running. Go with this.
All right, let me see here.
Can maximize it.
Yeah. So it's the same setup in this video. Premium at the top, expedited in the center, and best effort at the bottom. Let me just make it skip a little bit faster so we can get to the point where we left off here. File is going to be created. Yeah, I think here we're highlighting that we're just trying to say which one is which, premium, expedited, and best effort. And now we will start the test by creating this file. All right, so premium traffic at around 800 megabytes, expedited around 750, and the best effort, of course, is like about half of the others at around 450 megabits per second. And here, once the test was done, we'll see how much total bandwidth was transferred and at what rate. I think they run for about 30 seconds here. And yes, so 2.72 gigabytes transferred for premium, 2.5 for expedited, and 1.56 for best effort. And now I think moving on to the second part of the test, we're just going to clear these windows here. And then we'll start the best effort for about 60 seconds, so we'll start that first. All right, servers are started, starting the senders now. Best effort is now started. It's getting 1.3 gigabits almost. And then once we start the premium sender, we'll see the EDT at work here. So the premium sender just started, and the bandwidth of the best effort dropped dramatically. It dropped from, I think, 1.3 all the way down to 100 megabits per second. And the premium traffic here is taking up the majority of the bandwidth at around 1.4 gigabits per second. And now once the premium traffic is finished sending, we'll see the best effort come back up. And coming back up from 88 megabits per second back up to 1.3 gigabits per second. And that concludes the demo. Thank you. And I'll pass back to Vinay to explain the numbers and the graphs.
Thank you, Phu. Okay, we couldn't do the live demo, but we still had the video, thankfully. The demo gods were not smiling on us today. Okay, so it's a lot easier to understand what we saw if we look at it in a table form. What we saw, in fact, the first part of it, the QoS, the pod that controls the QoS was not running. So you saw all three get equal traffic in the earlier part of the demo, which was supposed to only show the second part with the QoS. So the results here are that when we have, without QoS, premium, expedited, and best effort, all three of them get a similar amount of bandwidth. They get a similar amount of data through. But with QoS, there is clearly a separation. The premium traffic is given more priority, followed by expedited, and lastly with best effort. The second part of the graph that you see here, the second part of the what you see here is in the orange line, that's the best effort traffic that was started without any other traffic in the picture. And then around a 10 to 15 seconds range, we start the premium traffic, which is this green line here. And as soon as the Mizar transit daemon bandwidth monitor detected that there is activity from premium traffic, it configured the BPF maps for the rate limiting to bring the amount of bandwidth available to best effort traffic all the way down to 10%. And that's what you see happening here, where the best effort is throttled all the way down here until the premium traffic is present. Once the premium traffic is done sending, the bandwidth is made available back again to the best effort traffic, and it picks up and goes back to the amount of bandwidth it was using before the premium traffic kicked in. So what's great about this is that to achieve all this, to get this overlay working, we had to do 0 lines of kernel code change. All this is happening in the kernel, but we had almost no code, we had no code that we had to put in the kernel, except the BPF programs. That is the appeal, that is the magic of eBPF. So with that, I will conclude our talk today, and we'll open it up for question and answers. We have a few of our resources here, the links to the projects that we've been working on, including Mizar, which is where we have implemented this QoS feature, the prototype of this feature. Thank you very much, and we'll take questions.
Thank you for the presentation. That was really good. I just wanted to know, what kind of permissions do you need to be able to run your daemon, especially in Mizar, and to run the scripts themselves?
So currently, we are running Mizar as a privileged pod, and we use the host networking mode, but we really did not invest a lot of time into getting it the minimum permissions that it needs. My take is that it can get by with, there are a few capabilities like cap BPF, cap sysdetadmin, and one more probably for resources. Those three should be sufficient. We just never had the motivation or time to invest into figuring out what is the right minimum set for these. But you do need to have cap BPF to be able to load BPF programs in the kernel. Besides that, everything else is pretty vanilla, I would think. I can't really think of anything else that requires special permissions. Any more questions? Okay, thank you very much. Thank you all for coming. Appreciate it. Thank you.